In this video lecture, we are going to see about the tuned amplifier. So even this amplifier, we are mostly familiar with it. So these are the amplifiers which are employed for the purpose of tuning, or that means which is the selecting a particular frequencies. So among the set of frequencies available, so if you need to select one particular frequency, while I don't want all other frequencies, then that I call it as a selection. So in that case, I can use a circuit which is called as a tuned circuit, so which will do the above process. When an amplifier circuit has its load replaced by a tuned circuit, such an amplifier can be called as a tuned amplifier circuit. So to amplify the selected range of frequencies, the resistive load RC is replaced by a tuned circuit. So the tuned circuit is capable of amplifying signal over a narrow band of frequencies centered at the resonant frequency, that is denoted by FR, which is given by 1 by 2 pi root LC. The amplifiers with such a tuned circuit as a load are known as tuned amplifiers. So we have certain parameters associated with the tuned amplifiers. The first is coil losses. So the tuned circuit consists of coil. So practically it is not purely inductive. Coils are not purely inductive. So this will lead to some losses, and they are represent the form of a leakage resistance in series with the inductor. So the coil can be indicated with the L, and you can see in the figure there is a indication of resistance in series with the inductor. The total loss of the coil is comprised of copper loss, eddy current loss, hysteresis losses. So the copper loss at low frequencies is equivalent to the DC resistance of the coil. So it is inversely proportional to the frequency. Eddy current loss in iron and copper oil are due to currents flowing within the copper or core cased by induction. Eddy current losses are directly proportional to frequencies. We have one more loss, which is an hysteresis loss, which is proportional to the area enclosed by the hysteresis loop and to the rate at which that loop is traversed. It is a function of signal level and increases with frequency. The second parameter is Q factor, which is a quality factor. This is a very, very important characteristics of an inductor. So this is a ratio of reactance to resistance, and therefore it is unitless. It is a measure of how pure or real an inductor. So in case that is the inductor contains only reactance. The higher the Q of inductor, the fewer the losses in the inductor. So the Q factor can also be defined as a measure of efficiency with which inductor can store energy. So we have one more term initiated over here, which is a dissipation factor D, that can be referred to as a total loss within a component, which is defined as quality factor equation Q is equal to 1 by D. So similarly, we have an unloaded and loaded Q. Unloaded Q is a ratio of stored energy to dissipated energy in a reactor or resonator. The unloaded Q of an inductor or capacitor is X by Rs, where X represents a reactance and Rs represents a series resistance. So the loaded Q of a resonator is determine how tightly the resonator is coupled to its terminal. So for this circuit, we can write the thing to be R0, which is omega naught L by QU, and similarly RC is omega naught L by QL. So the circuit efficiency for the above tank circuit is given by the above expression. So from this expression we can realize that for high overall power efficiency, the coupled in-load RC should be large in comparison to the internal circuit losses represented by R0 of the inductor. So the quality factor QL, that is loaded Q, determines the 3 dB bandwidth for the resonance circuit. So the 3 dB bandwidth can be given as FR by QL, where FR will be the center frequency of a resonator. If Q is large and the bandwidth is small, the circuit will be highly selective. So here QU represents unloaded Q and QL represents unloaded Q. So what are the requirements of a tuned amplifier? So it should provide selectivity of a resonant frequency over a very narrow band. So the signal should be amplified equally well at all frequencies in the selected narrow band. The tuned circuit should be so mounted that it can be easily tuned. If there is more than one circuit to be tuned, there should be an arrangement to tune all circuits simultaneously. The amplifier must provide the simplicity in tuning of the amplifier components to the desired frequency over a considerable range of the band of frequencies. So what are the advantages of going for a tuned amplifier? So we use the reactive components like L and C, which will minimize the power loss and which makes ultimately the tuned amplifiers efficient. The selectivity and amplification of the desired frequency is high by providing higher impedance at resonant frequency. And other advantages a small collector supply would do because of its little resistance in parallel tuned circuit. So however, it is important to remember that these advantages are not applicable when there is a high resistive collector load. So it can be classified as the cascaded stages of multi-stage tuned amplifier can be categorized as single tuned, double tuned, stagger tuned. Similarly, these amplifiers are further classified according to the coupling how we use it. So either it is a capacitively coupled, inductive coupled or transformer coupled. Thank you.